Welcome you all to Principles of Organic Synthesis. So far we had 12 lectures. In the first 9 lectures we studied about the carbon-carbon bond formation. Lecture 10 to 12 we have studied the carbon-nitrogen bond formation. Today we will start the electrophilic aromatic substitution. In this topic also we will have 3 lectures. In this lecture we will study the principles of the electrophilic aromatic substitution, then Friedel-Crafts reactions. As you can see here, the electrophile should be electron deficient. Usually they are represented as E plus, as you can see here. A that can be ion or a molecule, as you can see here. As you can see, a molecule or ion that accepts a pair of electrons to make a new covalent bond is known as an electrophile. It can be, as you can see here, these are some of the examples: nitronium ion, this carbocation, sulfonium ion. They can act as a electrophile, the electron deficient. Here an example shown, common representation for the aromatic electrophilic substitution. Look at here, you have benzene ring and the CH bond is converted into a new covalent bond with E, and this E represents the electrophile, and basically it first the benzene ring undergoes addition with the electrophile and followed by elimination of proton. So, it involves addition elimination reaction. At the end you can see in overall you substitute the electrophile in the place of hydrogen. It is a substitution reaction, aromatic electrophilic substitution reaction. This reaction usually performed in the presence of acid as catalyst. For example, we use Lewis acid often to speed up the reaction because it is a poor nucleophile. Aromatic benzene is a poor nucleophile. To speed up the reaction, we use acid as catalyst. Now, let us look at here the main classes of electrophilic aromatic substitution. Here an example shown for the halogenation reaction. These are the electrophile. For example, chlorination, Cl plus is acts as an electrophile, and this reaction usually carried out in the presence of Lewis acid like aluminum chloride, the FeCl3. For example, when you have so it has a lone pair, you have the Lewis acid, aluminum chloride. Say Lewis acid, it can now you will be able to form so activated electrophile. Now this one, once you form this one, now the benzene ring can undergo reaction. When you have this is benzene ring, it can now react with this activated electrophile and the substitution reaction can take place. Similarly, in the case of bromine also, if you have, for example, aluminum bromide, and if you have Br, you will be able to form, you can write like this. So, this is activated electrophile. Now, the benzene ring easily can undergo reaction with this bromine, and similarly sulfonation. And this can be formed if you have the sulfuric acid. We use usually sulfuric acid as catalyst in this reaction. So, when you know very well, when you have the sulfuric acid, you will be able to form O minus plus this can lose water molecule. You will be able to form So, this when you react with so this can remove this proton, then you will be able to form this sulfonium ion, which act as a electrophile, then you regenerate your sulfuric acid. So, this acts as a electrophile in this reaction. So, if you have sulfuric acid, one of the sulfuric molecule acts as a base, another one acts as an acid, then you will be able to form SO3, and which act as a electrophile in the sulfonation reaction. In this way, you can form the carbon sulfur bond. When you use chlorine or bromine with the presence of Lewis acid, you will be able to form the activated electrophile. In this way, you can make a carbon halogen bond. And is here the next example, nitration. This reaction is usually carried out again with sulfuric acid. If you have the nitric acid, and sulfuric acid, so this can now act as a base, can deprotonate, you will be able to form plus this one. This can lose water molecule, you will be able to form NO2 plus and water molecule. So, therefore, when you take nitric acid and in the presence of sulfuric acid, it can generate nitonium ion. So, in this way you can make the carbon nitrogen bond formation, nitration you can do in the aromatic system. The next example involves Friedel-Crafts reaction. So, you can generate, if you have alkyl halide. So, these reactions are usually carried out in the presence of Lewis acid, as we have seen the case of halogenation. In the presence of aluminum chloride or FeCl3, you can carry out the reaction, you can make a carbon-carbon bond, you can do alkylation acylation. For example, if you have alkyl halide, and when you react with aluminum chloride, as we have seen, now you can form and plus minus. So, this can act as a electrophile. Similarly, in the case of acid chloride, we have, for example, acid chloride, and if you have aluminum chloride. So, as you have the lone pair, this can, so you can push it and then you will be able to form acylium ion, which acts as a electrophile plus this acts as electrophile in this. Therefore, if you look at these are some of the main classes of electrophilic aromatic substitution reactions. We will study them in detail later. Here the general mechanism for the aromatic electrophilic substitution shown. First, as you can see here, the first step, this acts as a nucleophile. This is a weak nucleophile. It undergoes addition reaction. This addition, then you get this carbocation intermediate. Once you form this one, then the deprotonation takes place. The base removes this proton, then this is fast, this is elimination reaction, this elimination reaction, and you what you do here, you introduce the electrophile. In the place of this hydrogen, you have introduced the E electrophile. First step involves addition reaction, second step involves elimination by cleavage of the carbon hydrogen bond. So, overall if you look at here is a substitution reaction. Now, let us compare the aromatic electrophilic substitution with the addition reaction of alkene. Let us compare with the cyclohexene. of cyclohexene with bromine, it acts as a nucleophile. It is a strong nucleophile comparing to benzene ring, because of the aromaticity this benzene ring is more stabilized. So, it acts as a nucleophile, this acts as a electrophile. They will be able to form the brominium ion intermediate Br minus. The Br minus can react via SN2 pathway. Whether this carbon or that carbon, you will be able to form addition product. In this reaction, this double bond undergoes addition with this bromine, and first one, this acts as a electrophile, this acts as a nucleophile, then addition reaction takes place. When you react benzene with bromine, no reaction or very slow. So, this is because it is a poor nucleophile. On the other hand, as soon as you add Lewis acid, we have a benzene, and if you add Lewis acid, for example, FeBr3, the reaction readily takes place, you get the substitution product. There is no addition product observed. This is because if you look at the energy level of these reactions, if you see the energy level of this transition state, if you look at here, this is higher energy comparing to that. Therefore, the addition reaction is not favored in the case of aromatic system due to loss of aromaticity. But when you carry out the reaction by substitution, you recover the aromaticity. For you look at here, this is more stable benzene ring, this is a less stable the carbocation. When you make the substitution reaction, you will be able to recover the aromaticity, you generate a more stable substituted benzene. On the other hand, if you carry out the addition reaction, less you lose the aromaticity, you produce the less stable cyclohexadiene intermediate. This, if you look at this one compared to the benzene ring, this less stable. Therefore, when you have the aromatic system, they are prone to undergo substitution reaction compared to the addition reaction. And also, just I mentioned, if you compare the alkene and the benzene ring, this is good nucleophile, it can readily undergo addition reaction with the electrophile. On the other hand, this is a poor nucleophile because of aromaticity, and then you have to use acid as catalyst to activate the electrophile. Then this can undergo addition reaction followed by a cleavage of CH bond, and overall you end up with a substituted compound. So, the substitution, if simple benzene, and you will be able to introduce the electrophile. On the other hand, if benzene has already substituent, it can affect the position of the substitution. The rate of the reaction is strongly dependent upon the nature of the substituent present in the aromatic ring. Suppose if the benzene, this simple benzene ring, and so you will be able to form the substitution product. On the other hand, if already has a substituent, then it can direct the substitution at different positions. The relative ease of substitution at different positions in the aromatic compound is also determined by the nature of the substituent. Basically, the nature of the substituent plays crucial role in the electrophilic substitution. Now, let us look at, for example, you have substitution here, and once we have already substitution in the aromatic ring, the incoming electrophile can undergo reaction this carbon ortho position, then you get this 1,2 product. It can also undergo reaction this carbon meta position. So, in this way you will be able to form 1,3 product. It can also undergo reaction the para position, you will be able to form 1,4 product. There are 3 possibilities. You can form 1,2 product or 1,3 product or 1,4 product, that depends upon the X. The electronic nature of X plays crucial role to undergo the aromatic electrolytic substitution to give the product. For example, let us look at toluene. When you have the toluene, when you do the nitration, if you can look at here, we end up with a mixture of compounds. If you look at the ratio of this compound, the ortho nitration is the major product, then you get the para. Comparing to meta, these two are major compound. So, this can be easily understood if you write the resonance structures. So, as we have seen earlier, when you mix nitric acid with sulfuric acid, you will be able to form the nitronium ion, and now this can undergo addition reaction. For example, if it undergoes addition reaction in this position, ortho position, then you will be able to form these 3 resonance structures. If the ortho position undergoes substitution reaction with this NO2 plus, and you will be able to form these 3 resonance structure. On the other hand, if undergoes reaction with meta carbon, then you will be able to form these three resonance structure, the carbocation can be stabilized by these three resonance structure. If you look at here, this is most stable because this carbocation can be stabilized by the methyl group, and when you can write similarly to the nitration to para position. If you do nitration here, so if you look at here, this also so there are three possibilities you can see here. If the substitution takes place the ortho position and the para position, you can see here this resonance structure when you write these two are, this carbocation can be stabilized by methyl group. Therefore, comparing to if on the other hand the reaction takes place at the meta position, you can see you do not have that kind of stabilization. Therefore, when you have the electron donating group, this for example like methyl group, the nitration selectively takes place at ortho and para position comparing to the meta position. This can be easily understood when you write the possible resonance structure, and these are the responsible for the stabilization of the carbocation intermediate. When you write, then you will be able to predict why when you do the nitration with the electron donating group, always the ortho and para positions are favored comparing to meta position. This is a reason, and you can see here when you write the possible resonance structure for the ortho substitution and para substitution, you can see there is a resonance structure which can be stabilized by the electron donating group. So, methyl group tends to direct the electrophiles into ortho and para position. This is the reason for that selectivity. Now, let us go for the nitration with the nitrobenzene. Just we have seen the nitration with toluene. In this case, if you look at here, the ratio of the dinitro compounds, to see the compound that you form from meta position is a major compound comparing to that para and ortho positions. So, this also can be easily understood if you start drawing the resonance structures. When you react with the nitronium ion at the ortho position, and you will be able to form this intermediate. So, if you try to draw the resonance structure, so if the nitration takes place at ortho position, and you will be able to form this carbocation, which if you try to draw the resonance structure, there are three possible resonance structure. If you look at this is the least stable among this, because you have already electron withdrawing group, You have the carbocation next this carbon, and the same carbon has electron withdrawing group. Therefore, this resonance is very less stable when you draw the resonance structure. Now, let us go for the reaction with the meta position. If the nitration takes place at the meta position, so you will be able to form this carbocation, which if you try to draw the resonance structure or the stabilization of the carbocation, these are the possible resonance structure if the nitration takes place at the meta position. On the other hand, if reaction occurs at para position, so you will be able to have the following. So, these three resonance structure. If you look at here, this is least stable comparing to these two structures, and here similarly this is least stable comparing to these structures, and you do not have this problem. If the reaction takes place at the meta position, you do not have this kind of least stable intermediates. So, therefore, when you have the electron withdrawing group, the aromatic ring, always the electrophilic substitution is favored at the meta position comparing to the ortho and para positions. On the other hand, if you have the electron donating group, the reaction is facilitated at ortho and para position comparing to meta positions. This can be easily understood by drawing the possible resonance structures, and you can see here when you have the nitration, when the substrate, for example, the nitrobenzene, and you can see here, and if the nitration takes place meta position much favored comparing to ortho and para position, because, and you can see here you have the least stable intermediates when you draw resonance structures, and you can see this kind of least stable intermediate. Therefore, when the reaction selectively takes place at the meta position comparing to ortho and para positions. This table gives the summary of various substituents. For example, if you have the O minus and it has plus I and plus M effect, this usually the electrophilic substitution takes place ortho and para position is very powerfully activating group. This means this is inductive effect, this mesomeric effect. If it has a lone pair, it can you can try to stabilize through resonance structure, mesomeric effect you know very well. And this also you can, through inductive effect, you can facilitate the substitution reaction. So, these are the some of the examples you can see here, and already you know very well, and we will see many examples you can try to understand. And these are the electron withdrawing group. For example, when you have this, just we have seen if you have the nitro group, the reactions facilitated meta position you can see here. When you have the electron withdrawing group like ester, carboxylic acid, aldehyde, and ketone or cyano group, nitro, sulfonic acid, usually the reaction is favored at the meta position, And same thing if you have the NH3 plus or NR3 plus, and always the reaction takes place meta position. On the other hand, if you have the electron donating group like methyl, amide, and you can see here, and amino group, methoxy group or alkoxy group or halogen, and usually the reaction is favored predominantly ortho and para positions. Now, let us look at, just we had some idea, basic information about the aromatic electrophilic substitution. Now, let us see some example for the carbon bond formation. So, all of you know very well about the Friedel-Crafts reaction. Here an example shown for the alkylation. If you have the tetrabutyl chloride, you can try to react with benzene, the presence of Lewis acid, aluminum chloride, then you will be able to form a carbon bond. The mechanism of this reaction shown here, as we have seen, when you have the Lewis acid, it can form a activated intermediate. Once you form this one, then you will be able to form this carbocation. So, this carbocation now can act as electrophile. Now, the benzene can undergo reaction. As you can see here, then you will be able to form this carbocation intermediate. Once you form this one, now this can deprotonate, and you will be able to form the tetrabutyl benzene, and HCl is generated as a byproduct. You regenerate with the catalyst, though you need a catalytic amount of aluminum chloride to carry out the reaction. Therefore, if you have the alkyl halide and you can try to react with the Lewis acid, and you will be able to form a carbocation which acts as a electrophile. Now, the benzene can act as a nucleophile. It can undergo first addition reaction, as you can see, then elimination, cleavage of this carbon hydrogen bond, then you will be able to form tetrabutyl benzene via carbon bond formation. Here some examples shown for the Friedel-Crafts reaction. As you can see here, the first example involves the reaction of benzene with adamantyl chloride in the presence of aluminum chloride. As we have seen, this can undergo reaction. You will be able to form the corresponding tertiary carbocation, which can undergo substitution reaction with the benzene ring, and you will be able to make the alkylation, as you can see. And similarly, here on another example shown the reaction of chloroethane with the benzene. As we have seen, this also can undergo reaction. When you react with aluminum chloride, you will form this carbocation. Now, this can undergo reaction, as we have seen, and you will be able to form ethyl benzene as the product. Now, let us look at this one, 1,2-dichloroethane. This also, as you can see here, now the aluminum chloride can readily react with this one, and so you use 2 equivalent of benzene, then you can make this 1,2-diphenyl ethane as the product, as you can see here. And this, if you look at these examples, usually they utilize aluminum chloride as the Lewis acid catalyst for the alkylation reactions. You can also carry out the reaction. For example, if you have the alkene and the presence of acid, as we have seen, so it can act as an electrophile, it can as a nucleophile, then you will be able to form a carbocation. So, once you form the carbocation, now this can readily undergo reaction with the benzene. So, first addition reaction takes place. First, what you do here, you form the carbocation, the alkene undergoes, the cyclohexene undergoes addition reaction with the proton, then you form the carbocation which acts as an electrophile, which can now react with benzene. You form this carbocation intermediate. Now, this can react this base, it can deprotonation takes place. So, once you form this one, now this can act as a base, removal of this proton, and then you will be able to form the cyclohexyl benzene as a product. Similarly, in this case also, in the presence of acid, you can form the carbocation which can undergo cyclization, you will be able to form the tricyclic system as the product. So, these reactions, these are example for the alkylation reactions. If you have alkene, then also in the presence of acid, you can make a carbocation which can act as a electrophile that can readily undergo reaction with aromatic systems, you will be able to form the alkylated compound. Here an example shown, these all are very straightforward reactions. If you look at this reactions, it involves a rearrangement in the presence of Lewis acid, what happens. And for example, when you react benzene with this alkyl chloride in the presence of Lewis acid, and we will be able to form this as the product. In this case, and this alkyl halide first reacts with aluminum chloride, and we form the carbocation as just we have seen. Once you form the carbocation, there is a 1,2 methyl shift involves, then you form the this. If you look at here, the primary carbocation is converted into tertiary carbocation, which is more stable. Once you form this carbocation, now this undergoes reaction with your benzene ring. So, then the addition followed by elimination takes place to give this as a product. So, in this case, and you form the primary carbocation which undergoes rearrangement to form a more stable tertiary carbocation which acts as electrophile. Therefore, in the case of aromatic electrophilic substitution, when you carry out the reaction with alkyl chloride or alkyl halides, and in the presence of Lewis acid, they can readily undergo rearrangement, depends upon the nature of the substrates. You will be able to form a more stable carbocation intermediate that can act as a electrophile to give substitution product. Now, let us take this an example, benzene with this alkene. So, in the presence of acid, there is a two possibilities there. When you take this alkene, then you will be able to form on the other hand. So, in this way you form the secondary carbocation as the intermediate. On the other hand, if the alkene reacts the other way, it will be able to form there are two possibilities there. And if you look at, if you do the reaction with the benzene ring, and since this is a primary carbocation, less stable comparing to the secondary carbocation, therefore, whenever you do the reaction, and you will end up with this as a major compound. And similarly, here this when you form the primary carbocation in this case, and it undergoes rearrangement to form the more stable carbocation, which undergoes reaction with this aromatic ring to give this substitution product. Now, let us look at an example for the acylation reaction. As you can see here, here the reaction of acetyl chloride with the benzene, the presence of aluminum chloride is shown, and you can make the acetyl benzene as shown here. This is very common method we use for the acylation of aromatic systems. As we have seen just now, this can make chelation as we have seen earlier, and you will form the activated electrophile, then you push it here, and then you will be able to form the acyl ion. Once you form this electrophile in this reaction, now it can undergo addition reaction, then you will be able to form this intermediate. Once you form this intermediate, and this can deprotonate this proton, then you will be able to form the acylation product. And as you can see here also first involves addition reaction and then elimination, cleavage of this carbon hydrogen bond gives this substituted compound as the product, and some examples are shown as you can see. So, similar way, just here we have seen the reaction of acetyl chloride with benzene, the presence of aluminum chloride, you can get the acetyl benzene as the product, and here the reaction of this acid chloride, the presence of aluminum chloride shown here, as we have seen there, it can form the corresponding so acyl ion intermediate. Once you form this one, which can readily undergo reaction with your aromatic ring, then you will be able to form this ketone as the product. Similarly, you can also carry out acylation in this substrate, and the presence of aluminum chloride, you can make this ketone. You can see here, these all are intermolecular reactions. The reaction of acetyl chloride with benzene gives the acetophenone as the product. You can see here the reaction of benzene with propanyl chloride shown, you give the corresponding ketone as the product. Here again the reaction of acetyl chloride with this system is shown, you can make this ketone as a product. All are intermolecular reactions. This is an example for intramolecular reaction. If you have the acid chloride, you can also react with Lewis acid. It can undergo intramolecular cyclization, as you can see here, you will be able to form this bicyclic ketone. And this another example, this is also for intermolecular reaction. If you look at all this example involves acid chloride as acylating agent. Usually we use acid chloride as acylating agent. In addition to that, you can also use acid anhydride as acylating agent. This is an example. If you have this anhydride, you can try to readily react with aromatic system. In the presence of Lewis acid, you will be able to form the keto compound, and this also can be further, you can convert into the presence of phosphoric acid like this. You use phosphoric acid, then you will be able to convert into further ketone as a product. Now, let us look at, in summary, today in the first part we have seen the principles of aromatic electrophilic substitution reactions, and we have seen the reaction involves addition followed by elimination. You get the substituted compound, and if you compare, then we also have seen the reason for the aromatic compound to undergo substitution reaction comparing to the alkenes. If you look at the alkene which undergoes addition reaction, on the other hand, if you have the aromatic system which leads to substitution reaction, this is because to recover the aromaticity. Then we have seen the effect of a substituent, the aromatic electrophilic substitution reaction. For example, if an aromatic system already has a substituent, it can direct the electrophilic substitution reaction at ortho or meta or para position. This can be easily understood by drawing the resonance structures of the carbocation intermediate. If you have the electron donating group, usually the electrophilic substitution takes place at ortho and para positions. The reaction is facilitated, the rate of the reaction is enhanced because of the electron donating effect of the substituent. On the other hand, if we have the electron withdrawing group like nitro group, the reaction electrophilic substitution is facilitated at the meta position. The reaction is very slow because benzene is poor nucleophile. If we have the electron withdrawing group, the nucleophilicity of the benzene ring is further decreased, therefore, the reaction is less favored, and the reaction usually takes place at the meta position. Then we have seen Friedel-Crafts reaction for the carbon-carbon bond formation. We have seen the alkylation reaction with some examples. Similarly, we also have seen some example for acylation reactions. With this, we conclude this lecture. Thank you very much.